What's up, guys? It's Mr. Bringle, and today we're going to be talking about the constant velocity particle model worksheet number 2. Okay, so in the first one, you learned about position versus time graphs and then velocity versus time graphs. We talked about with little dudes 2. And so you've kind of had an introduction to that, and now we're going to build off of it. Okay, so let's go ahead and jump right in here. We are going to look at these. We've got motion maps and we've got actual velocity versus time graphs. And so this won't zoom in for me. Not sure why. So what we're going to do here is we're going to look at the prompt. For instance, in number 1, it says the object is moving in the positive direction at a constant, steady speed. So we are not only going to make a motion map for this, but then we will also put this on the velocity versus time graph so we can see both of them together. Okay. So all this says is that it's moving in the positive direction at a constant speed. It does not specify where the object starts in terms of position, and it does not specify how fast it's moving. So we can be very generic about this. I'm just going to make things easy, I'm going to start it at 0 meters. If you're completing this on Cami, make sure to use your little dots and line tools when we're doing this so it looks nice. But we'll start right there. And then it just says it's moving at a constant steady speed in the positive direction. So notice that this is defining to the right on this arrow as the positive direction. So this would be like 1 meter, 2 meters, 3 meters, 4. So what I'm going to do here is I'm going to make this going 1 meter per second. And we'll just go to right there. Okay. So remember that the first dot is always 0 seconds, and then 1 second, 2 seconds, 3 seconds, and 4 seconds. And that we need to show arrows that are basically implying how fast the object is moving. Okay. And these should all be equal, right? Because it's traveling at 1 meter per second based on the way that I drew it. Okay. So again, for the velocity versus time graph, we don't know exactly how fast it's going. All we know is that it's moving in the positive direction. So if this is 0 right here, this would be the negative side. This would be the positive side of the graph. So as long as you draw this as a line on the positive side, we're good to go. Now, it says it's constant velocity. So on a position versus time graph, a constant velocity looks like that, right? You've got a straight diagonal line. That would be constant velocity on a position versus time graph. But I want you to be careful here, because if we were to, put numbers right here and do, 1 meter per second, 2 meter per second, 3 meter per second, 4 meter per second, right? That is, this line that I've drawn right here is actually showing you that the velocity is increasing, right? The velocity is changing when we draw the line like that. So we don't want that because it says constant velocity. So what we need to do is we need to draw a horizontal line. Since I put 1 right here and we said it was moving at 1 meter per second, I would draw a horizontal line like this. Okay. So obviously mine's a little wavy, but that should be a flat line. This is implying that the object is moving at 1 meter per second the entire time, right? At 0 seconds all the way to 10 seconds, the object moves at 1 meter per second. Okay. So we'll go ahead and move on now. So in the second one, it says the object is standing still. Again, it does not tell us exactly where this is happening, so it does not matter where you put it on the map. I'm just going to go at 0 meters. And to show that an object is not moving over some period of time, all we have to do is stack the dots. Okay, so what this is saying is that at 0 seconds, 1 second, 2 seconds, and 3 seconds, the object is always at 0 meters. It has not moved. Okay, so the way to show that on your velocity versus time graph, remember this midline here is 0. This would be a negative velocity, which remember is just telling you direction. Positive velocity, just telling you direction. So we would draw this line. I'm going to draw mine kind of squiggly to make sure that you can see it, but this line would go like this. In fact, you know what? We'll just go with a yellow line so it pops out. And we'll just draw that line right on 0. And I'm going to draw it a little bit thicker here. Okay, so we just draw that right on 0. Object's not moving. Okay, so now let's move on to number 3. The object moves in the negative direction, so now it's telling us some other things here. So negative direction at a steady or constant speed for 10 seconds, and then it holds still for 10 seconds. Now, because that's a lot of dots to put on here, 10, that would be 20 dots. What I'm going to do for this one is I'm going to say that each dot represents a 2-second time interval on this graph. So we normally just do 1 second per dot, but we'll do 2 seconds for this one just so there's not a billion things on here. So let's go ahead and talk about the negative direction, right? So this is the positive direction over here, which means that it would need to be moving backwards towards 0 to get toward the negative direction, all right? So what we're going to do is we're going to start the object back here. Again, doesn't matter exactly where we start it because it just says it moves in the negative direction. So we'll say, remember, this starts at 0 seconds, and we're going to go by 2 seconds, so we need to be careful here. So this is going to be 2 seconds, 4 seconds, 6, 8, and 10 right there. So let's go ahead and draw this. So it's moving at a constant speed in the negative direction. So we'll get our arrows on here. They should all roughly be the same size. Okay. This would be 1 second, 2 seconds, or I'm sorry. I see, it's easy to mess up. 2 seconds, 4 seconds, 6, 8, and 10 right there. So it does say that it moves at that constant steady speed in the negative direction for 10 seconds. So we would stop right there. And then it stands still for 10 seconds. So we're going to stack the dots. That would be 12, 14, 16, 18, and I'm going to squeeze 20 on there. Okay. So 12, 14, 16, 18, and 20. Okay. So make sure you label the times on there. If you don't, inevitably what ends up happening is people write the wrong time for that first one, and then you end up 1 dot less than what you should have. And we'd be ending it at 18 seconds instead of 20. Okay. So now we need to show this on the velocity versus time graph. So it's moving in the negative direction. We haven't had one of those yet. So remember, that's supposed to be a plus sign up there. Remember that a negative velocity just tells you that the object is moving in the negative direction, right? It's a speed, and then that negative sign tells you direction. So what we're going to do here is I'm going to split this in half as best I can here. This probably won't be exact, but that dotted line, that's going to be our halfway point. So we'll say that that's 10 seconds right there, and then the remaining time would be 10 seconds as well. So all I'm going to do is I'm going to show that this object has some constant negative velocity to start off with. Okay, so we need to draw a flat horizontal green line here on the left part of the dotted line. And then for the final 10 seconds, the object is standing still. It stops. So again, we want to put that line right here on 0. So I'm going to try to make this thick so that you guys can see that. Okay, so flat line somewhere in the negative region on the left side of the dots, implying that the object's moving at a negative constant velocity the entire time for 10 seconds. Then it stops for 10 seconds, and we draw that line up here on 0. Okay. All right, moving on here to our last one of these. It says the object moves in the positive direction at a steady speed for 10 seconds. It then reverses direction and moves back toward the negative direction at the same speed. Okay, so that's key here. It's moving in the opposite direction. It says the same speed. So what that's implying is that when the object is moving forward, when it's moving forward, let's say at 5 meters per second, when it turns around and reverses directions, it's also going to be moving at 5 meters per second, just in the opposite direction. Okay, so the speed part is important there because it's going to tell us how far apart our dots need to be. So let's go ahead. So for 10 seconds, I'm going to go ahead and say that 1 dot is equal to 2 seconds on this one, because 10 seconds is a long time. So we're going to start right here. This is 0 seconds. And we're going to move in the positive direction for 10 seconds. So this would be 2, 4, 6, 8, 10. Okay, let's draw our dots or our arrows. Okay. All right, now it says that at this point it reverses direction, moves back toward the negative direction at the same speed. So I'm going to change my color here to blue since I underlined that other stuff with blue. Now, what most people are going to do is they're going to just drop this dot down here and start going from there. You actually don't want to draw that dot because remember, if we go up here and we label these as 1 second, 2 seconds, 3 seconds, I've done it again. I'm used to doing the 1 second intervals. So we'll go 2, 4, 6, 8, and 10. If you stack that dot right there, this is the 12th second right there. And so that's implying that it stayed still. It stayed in the same position for 2 seconds, right? From 10 to 12. So we can't put a dot down there like that. So instead, what you're going to do is you're just going to show the arrow like this, okay, and put the next dot right there. So that would be the 12th second at that moment. So sometimes they'll leave this dot right there. They'll leave that there and just draw this arrow like I've done. Some people will move the dot. They'll basically not have the dot here and they'll just put it here instead. So this space would be empty right there. So it would look like that. Okay, that would also be fine if you do it like this. Okay, so just want to show that the object gets to 10 meters or whatever position this is at 10 seconds, and then it turns around and goes the other way. We don't want to stack those dots because if we stack them, then it would be just like this right here up above in the last problem right there. That implies that the object is standing still. So anyway, it goes in the negative direction, then remember it says the same speed. So we're going to put the dots in the exact same positions here because it should be moving same speed and get back to the same exact location at 20 seconds. It doesn't say it goes for 10 seconds. I am just going to go ahead and assume 10 seconds and have it go back to the same spot. Okay. So, let me split this in half again, and we'll just say that dotted line represents 10 seconds. So for the first part, the object is moving in the positive direction. So we'll just make a horizontal line like this on the positive side. And then because it says it's moving at the same speed in the negative direction, we basically need to make this line down here the equivalent. So like the space from here to here should be the same as the space from the midline down to where that one starts. Okay. So this is implying, let's say that this up here is like positive 2 meters per second. And then down here, this would be negative 2 meters per second. Okay. So we are now done with the first page, motion maps and some velocity versus time graphs there. And you can take a look at that, go back through it if you need to. We're going to go ahead and move on to the next page. Okay, so here we've got some position versus time graphs, and we're going to turn them into velocity versus time graphs. So this will help you see the difference between these two things, right? Because in this first one, what we've got is a constant velocity, right? So this is constant velocity for position versus time graph, okay? And then on this side over here, we've got velocity versus time. And we also need to show that it's a constant velocity, right? So on this one here, we can see that the object moves 1 meter after 1 second, 2 meters after 2 seconds, and so on and so forth. So this object is moving at 1 meter per second, okay? Now we want to put this on our velocity versus time graph. This time it does have numbers on it, so we are going to be specific. If it is moving at 1 meter per second, we want to draw a horizontal line right here on positive 1 meter per second. If that slope was negative, we would do it on the negative side of the velocity versus time graph. So just looking at this, very apparent, obviously, that the constant velocity on position versus time is angled, whereas constant velocity on the velocity versus time graph is horizontal. It gets mixed up a lot, so want to make sure that we get that straight, because a horizontal line on a position versus time graph, like if we drew this over here, just implies that the object stays in the same position the entire time and does not move. So moving on here, let's look at this next one, number 6 and then number 7. And here we go. So the object starts off at 0 seconds, it's at 2 meters. And then at 1 second, it's at 3 meters. At 2 seconds, it's at 4 meters. So this first part is 1 meter per second, constant velocity. Okay. So that's up to 2 seconds, right? At 2 seconds. So what I'm going to do for this first part is I'm going to show that the object is moving at 1 meter per second for 2 seconds on the velocity versus time graph. Okay. So right there. Now for the second part, we can see that after 1 more second, the object is now down at 2 meters, and then 1 more second, 0 meters. So now this one is moving at negative 2 meters per second, right? Because it's gone down from 4 meters to 2 meters in 1 second. So what we need to do is then show that for the last 2 seconds, the object moves down here on the very bottom of this graph at negative 2 meters per second. Okay. So, and I normally you just draw a line on there. I'm trying to make this thick so that you guys can see it, but don't go crazy with that. Okay. So, and some people like to do this. They like to basically connect the lines like that. That's not necessary. You can just leave it like this, because this just implies that the object immediately turns around at 2 seconds and moves in the negative direction. Okay. All right. So on number 7 here, number 7, again, for the first second here, so for 1 second, that is where we are going to have our change in velocity. But for the first second, it did move 2 meters, so positive 2 meters per second for the first part. And then for the second part, you can actually see that it goes 1 more meter, so it gets up to 3 meters, but it takes 2 seconds to do that. So from 1 to 3 seconds, it goes 1 meter. From 3 to 5 seconds, it also goes 1 meter, right? So that means that this is going to be a 0.5 meter per second slope. And you can calculate that if you'd like to, but 1 meter over the course of 2 seconds would be a half meter over the course of 1 second. So on our velocity versus time graph, we will start for the first second with 2 meter per second, positive 2 meter per second velocity for 1 second. And then from that point on, it is going to be moving at a half meter per second. That was a terrible line. Half meter per second. And I also drew it on the wrong side. So right there. Okay, so that would be the velocity versus time graph that matches up with this position versus time graph. All right. Now let's take a look at some of these analysis questions here, and we will finish things up. Okay, so it says for many graphs, both the slope of the line and the area between the line and the horizontal axis have meanings. Okay, so the area between, I would like to highlight this, the area between the line and the horizontal axis. What that is talking about is when I draw, it's basically talking about this space right here. The line between, or the space between the line that you drew and the horizontal axis. Okay, so even if that line was negative, like in the one above here, we would be talking about, this space right here, and then this space right here. Okay, so the area between the line that you drew and the horizontal axis is what we're about to kind of talk about here. So just kind of showing you what that means. All right, so it says, what does the slope of a position versus time graph, so position time graph, tell you about the motion of the object? Well, that we know that tells us the velocity of the object, right? That's nothing new. Okay. Now, looking at the velocity versus time graphs, determine the units for a square area on the graph. Actually, before we do that, on this last question, if you're following along, I want you to put a slash here and then put I want you to say for a velocity versus time graph, what does the slope mean for a velocity versus time graph? Well, we don't have to get into this in too much detail. I just want you to know that the slope tells you the acceleration. Okay, we'll get into this in our next unit, and we'll dive into that a lot deeper. But slope of a position versus time graph is velocity. Slope of a velocity versus time graph is acceleration. So all of our graphs here had flat lines, right? So if it has no slope, it has no acceleration. But we will eventually get into ones that do. Okay. So looking at this next thing, looking at the velocity versus time graph, determine the units for a square area on the graph. So if let's just look above here, I'm going to kind of draw a square around this. I'm going to put this square in blue right here. Okay, one square area. So basically, what I'm getting at here, I'm going to draw a square right here. Okay, and on the left side or on the either side, what are the units on that side, right? So if we're looking at the y-axis of this graph, what are the units? Well, it's meters over seconds, right? So that's what's on the y-axis. Now on the x-axis, we have units of time, okay, or units of seconds for time. Okay. So if we were to calculate the area of that square, you would tell me that area is length times width, right? So what happens if we just multiply the units of the length times the units of the width, right? So we would have our y-axis units, meters over seconds, times our x-axis units of seconds. I'll write seconds over 1. Okay, so then you can see that the seconds are going to cancel, and the only thing that we're left with is m, which is meters, right? Meters. So what does that mean, right? Okay, so this next question says, what does the area under the velocity versus time graph tell you about the motion of the object? Well, if the area has units of meters, what do we measure in meters? It would be distance or displacement, right? We're talking about velocity, so in this case, it would be displacement. So this tells you delta x, which is displacement. Okay. And if we actually look at that equation, so I'm going to put this kind of off to the side here, but velocity is equal to delta x over delta t, right? Well, let's multiply both sides by delta t. So the change in time, okay? These will cancel. And then what we're left with is that delta x, or displacement, is equal to velocity times the change in time, right? Okay, well, what did we just do in question B there? We multiplied velocity times time, right? Meters per second times seconds. That would be velocity times time. So that is the equation for displacement. So if I gave you a velocity versus time graph and said, calculate the displacement of this object, all you have to do is find that area underneath the or in between the horizontal line that you drew and the midline, 0, okay, the horizontal axis. So, just kind of, we're done with this worksheet, but just kind of looking at this, like if I wanted to calculate the displacement of the first 2 seconds of this graph right here, I would take the area of this area right here from the green line on 1 meter per second for 2 seconds, right? So the area would be 1 meter per second times 2 seconds, right? So we know that that's going to end up being 2 meters because these will cancel, and 1 times 2 is 2. And that should make sense, right? We can confirm that by going back over to our position versus time graph, and we see the object starts at 2 meters and ends at 4 meters after 2 seconds, right? So that's just another way to calculate displacement. All right, so that'll do it for constant velocity particle model worksheet number 2. Make sure to ask any questions when you get back in class that you might have.